Hello friends, welcome to my lecture on surfaces orthogonal to a given system of surfaces. We know that angle between any two surfaces at a point of intersection is the angle between their respective tangent planes at that point. Now let us say, suppose we are given a one parameter family of surfaces, we can write its equation as f x y z equal to c, where c is a parameter. Our aim is to find a system of surfaces which cut each of these surfaces at right angles, or you can say which cut each of these given surfaces orthogonally. Now we know that if we are given a surface f x y z equal to c, then gradient of f is a vector normal to the surface, okay, and gradient of f is I f x j f y k f z. Okay. So the normal at any point x by z to the surface f x y z equal to c has direction ratios f x, f y and f z. Let us assume that the surface z equal to g x y cuts each surface of the given system orthogonally. We can write z equal to g x y as let us write f x y z equal to g x y minus z equal to 0. Then the surface f x y z equal to 0 has normal with direction ratios of the normal to the surface f x y z equal to 0 are given by f x, f y, f z. Now f x is equal to the derivative of g with respect to x, f y is equal to derivative of z, derivative of g with respect to y, and partial derivative of f with respect to z is minus 1. Now let us note further that z is equal to g x y gives the partial derivative of z with respect to x as g x and partial derivative of z with respect to y as g y. Okay. So hence from these equations we get the partial derivative of f with respect to x as derivative of g with respect to x, which is z x, and similarly partial derivative of f with respect to y, which is derivative of g with respect to y, and derivative of g with respect to y is z y. And partial derivative of f with respect to z is minus 1. Okay. Now let us look at this equation. Since both the surfaces z equal to g x y and the given surface intersect orthogonally at the point of intersection x y z, their respective normals are perpendicular. So we must have f x into z x plus f y into z y minus f z equal to 0, and this equation is a Cauchy linear PDE because we can write it as this equation. This equation can be written as into P derivative of f with respect to x into P derivative of f with respect to y into Q equal to derivative of f with respect to z. So f x is the partial derivative of f x by z with respect to x which we can find from the given equation of the surface, and this is f by x by z into q equal to, then this is partial derivative of f x by z with respect to z. So, this equation can be interpreted as a first order PDE, f x into p plus f y into q equal to f z into f z. Hence, the integral surfaces of the equation 2 are orthogonal to the given system of surfaces, that is they are given by equation 1. Now, thus we can say the integral curves orthogonal to 1 are generated by the integral curves, integral surfaces orthogonal to 1 are generated by the integral curves of the characteristic equations dx upon f x, dy upon f y, dz upon f z. This follows from the fact that this equation is a Cauchy linear PDE. Now, let us consider, so then we will solve this characteristic system to arrive at the integral surfaces that are orthogonal to 1. So, let us now consider a system of surfaces given by x square plus y square plus z square equal to c x y, where c is a parameter. So, we shall first write it in the standard form f x by z is equal to c. Okay. So, if you want to write it in that form, then if f x by z equal to c, then f x by z will be equal to x square plus y square plus z square divided by x y. Okay. Now, let us find the partial derivatives of f with respect to x y z. So, f x is equal to, now this is what, x square upon x y, I can write it as x over y. Then y square upon x y, I can write as y over x, and z square upon x y, I will write just like that. Okay. So, what I will get, when I differentiate it partially with respect to x, I get 1 over y, and then partial derivative with respect to x will give minus y upon x square. Here partial derivative with respect to x will give z square upon 1 over x gives minus 1 upon x square. So, minus x square y. So, this is 1 over y minus y upon x square minus z square upon x square y. This is partial derivative of f with respect to x, then partial derivative of f with respect to y we can write. So, minus x upon y square, and then here we get 1 upon x, here we get with respect to y. So, minus z square upon x y square. Partial derivative of f with respect to z is equal to this is 0, this is 0, here we get 2z upon x y. So, the characteristic equations are dx over f x, dy upon f y, dz upon f z, which will give us f x is equal to this. So, dx over 1 upon y minus y upon x square minus z square upon x square y equal to d by over f y. So, minus x upon y square plus 1 over x minus z square upon x y square equal to dz divided by 2z over x y. This is what we get. Okay. Now, we can simplify this, or so this here if you take LCM, it is x square y will go up there. I can write x square y of dx divided by x square y. When you multiply here, you get x square y. So, this is minus y square, and x square y, so this is minus z square equal to, here x by square we multiply in the numerator and denominator. So, x by square dy divided by x by square gives minus x square, here we get plus y square, and here we get minus z square, and here what we get x by dz divided by 2z. Okay, or I can write it as, so cancelling xy we get x dx over x square minus y square minus z square is equal to y dy upon minus x square plus y square minus z square equal to dz upon 2z. Okay, from here what do you notice? This gives you, we multiply in the numerator by x, in the numerator here by y, here by z, we get x is okay, we write, we multiply here by 1, here by 1, okay, and then add z times here, z times dz. So x dx plus y dy, okay, plus z dz is equal to 0, because this is what you can see, this gives this is equal to x dx plus y dy plus z dz. This is equal to x square minus y square minus z square minus x square plus y square minus z square. We are multiplying here by z, so we get 2z square and the whole thing cancels. So x dx plus y dy plus z dz equal to 0, which implies x square by x2 plus y square by 2 plus z square by 2 is a constant. Okay, so we can write x square plus y square plus z square equal to some constant C1. Okay, now let us find another solution of this, and for that what we will do, x dx minus y dy, what do we get? X dx minus y dy will give you x square minus y square minus z square, and we are subtracting this one, so we get plus x square minus y square plus z square equal to dz upon 2z. Okay, so what do you get? X square, okay, this will add up, we'll get z square cancel, or this will give you x dx minus y dy over 2 times x square minus y square equal to dz over 2z. Okay, so this cancels with this, and what do you get? If you take x square minus y square equal to t, then you have 2x dx minus 2y dy equal to dt. So this is equal to, this gives you dt by 2t. Okay, x dx minus y dy is dt by 2, so dt by 2t equal to dz by z. Okay, or we can say ln t, this 2 I can multiply here, so ln t is 2 ln z, okay, plus some constant ln c2, so t is equal to c2z square, or x square minus y square is equal to some constant c2 times z square. Okay, so we get one solution as x square plus y square plus z square equal to c1, another solution as x square minus y square equal to c2 times z square, or we can say x square minus y square upon z square equal to c2, and therefore the general system, therefore the general solution is given by some function phi of x square plus y square plus z square and x square minus y square over z square equal to 0, because we know that if u x y z equal to constant, and bx by z equal to constant are two independent solutions of the characteristic equations, then general solution is phi u v equal to 0. General integral is phi u v equal to 0. So, using this result, okay, the general solution of the given system is phi x square plus y square plus z square and x square minus y square over z square equal to 0. So, this is what we get, this solution. Okay. Now, let us go to another question where we take a system of surfaces given by the equation z into x plus y equal to c times 3z plus 1. C is a parameter. Now, here we want to find a particular surface, okay, which intersects the surfaces of the given system orthogonally and passes through this curve. Okay. This curve is a circle which is given by the equations x square plus y square equal to 1, z equal to 1. So, the circle lies in the plane z equal to 1. So, here let us write this equation in the standard form f x by z equal to c. So, f x by z equal to z times x plus y divided by 3z plus 1. So, f x let us find first here, f x is equal to z over 3z plus 1, f y let us find, which is also z over 3z plus 1, and when we find f z, what is f z? In the numerator we have z, in the denominator also we have z. So, let us differentiate in the by the quotient rule. So, derivative of this with respect to z is x plus y into 3z plus 1 minus derivative of the denominator is 3 times 3 and then times numerator divided by 3z plus 1 whole square. So, what do we get? So, this is x plus y times 3z plus 1 minus 3z. So, we get x plus y divided by 3z plus 1 whole square. Okay. So, what do we get here? The characteristic equations are dx over fx, that is dx over z upon 3z plus 1, dy upon fy, which is z upon 3z plus 1, and dz over fz, which is x plus y divided by 3z plus 1 whole square. Okay. Now, taking the ratio, first ratio and second ratio, okay, we have dx upon z times 3z plus 1 equal to dy upon z upon 3z plus 1. This gives you dx upon 1 equal to dy upon 1 when we take the first and second ratios. So, this gives you x equal to y plus c1 or x minus y equal to c1. Okay. Now, let us from the characteristic equations 1 imply that dx over 1 is equal to dy over 1 equal to dz 3z plus 1 whole square over x plus y, and I am multiplying by z over 3z plus 1. So, I get this. Okay. So, this cancels with this and we have dr dx over 1 equal to dy over 1 equal to 3z square plus z into dz divided by x plus y. This is what we get. Now, this is further equal to, I multiply this by x, so x dx, I multiply this by y dy, and then I subtract, multiply it by minus 1. So, minus 3 z square plus z into dz, and in the denominator what we get, x plus y minus x plus y. So, this cancels with this, and what we get is x dx plus y dy is equal to r minus 3 z square plus z dz equal to 0. Now this will give you when we integrate, this will give you x square by 2 plus y square by 2 and then minus z cube minus z square by 2 is equal to some constant. Okay, multiplying by 2 I get another solution x square plus y square minus 2z cube plus minus 2z cube minus z square equal to some constant, let us say C2. Okay, now C1 is so C2 is phi C1, some constant C2 is phi C1 where C1 is an arbitrary function. So I can write it as phi of x minus y because x minus y is equal to C1. Now let us use the initial condition, that is the curve we have to find that surface which passes through this circle. So when the surface passes through this circle, x square plus y square is equal to 1, so 1 and z equal to 1. So we get 1 minus 2 minus 1 is equal to phi of x minus y. Okay, so this is phi of x minus y is equal to minus 2, and therefore I get these required surfaces x square plus y square minus 2z minus 2z cube minus z square is equal to minus 2, or x square plus y square equal to 2z cube plus z square minus 2. That is the surface which passes through the circle x square plus y square equal to 1 and the plane z equal to 1 and intersects the given surfaces orthogonally. So that is the answer. Now one more question we can consider where we have taken this system of surfaces, family of surfaces z equal to cxy x square plus y square, and this family of surfaces we have to find that surface which is orthogonal to this family and passes through the hyperbola x square minus y square equal to a square z equal to 0. So here again fxyz we can write fxyz is equal to z over x into y x square plus y square is equal to c. So let us find fx derivative with respect to x. When we differentiate with respect to x, we get minus z upon x square y square x square plus y square whole square, and then we have x cube y. So we are differentiating with respect to x. So 3x square y and then x by cube. So we get by cube. Okay, and then we have fy similarly. So minus z upon x square y square x square plus y square whole square. Okay, and then we have derivative with respect to y. So we have x cube derivative with respect to x cube and then x by cube. So 3xy square, and fz similarly. Fz can be written as 1 over xy into x square plus y square. So let us write the characteristic equations. They are dx over fx. So we have minus z upon x square y square x square plus y square whole square 3x square y plus y cube dy over minus z upon x square y square x square plus y square whole square, and then we have x cube plus 3xy square, and then we have dz over fz, which is 1 over xy into x square plus y square. So what we will do is I can write it as or x square y square x square plus y square whole square, it will go up, x square y square x square plus y square whole square divided by minus z times 3x square y plus y cube. Let us write like this dx, and then we have x square y square x square plus y square whole square divided by minus z times x cube plus 3xy square. And here what we have, this is dy, and here we have xy into x square plus y square into dz divided by 1. Okay. So what we do, we first divide by x square y square x square plus y square whole square. Let us divide that. Okay. So we get dx upon minus z, and here also I can take by common, so minus by z, and then we have 3x square plus y square. Okay. And here x square y square x square plus y square whole square we divide, so we get minus dy over minus xz times x square plus 3y square, and we are dividing by x square y square x square plus y square whole square, so we get dz upon xy into x square plus y square. Okay. Now what we do, we multiply by x by z in the numerator. So if we do that, we have x dx divided by we are multiplying by minus x by z, so dx x dx upon 3x square plus y square, and then we have dy over x square plus y dy over x square plus 3y square, and here we get x by z minus x by z, so minus z dz divided by x square plus y square. Okay. Now what we do is when I add x, this one and this one, I get 4 times x. Okay. So this gives you, okay, let us go to the next page. So we get this x dx upon 3x square plus y square equal to y dy over x square plus 3y square equal to minus z dz over x square plus y square. Now from here what do you notice? X dx plus y dy divided by 4x square plus 4y square. So 4 times x square plus y square is equal to minus z dz divided by x square plus y square. So these two cancel out, and we get x dx plus y dy equal to minus 4z dz. This gives you an integration x square by 2 plus y square by 2 equal to minus 2z square plus some constant, but you multiply by 2 and you get x square plus y square plus 4z square equal to some constant, let us say C1. Okay. So this is one solution. Another solution let us find. So we subtract now x dx minus y dy. Let us consider this, and you see that 3x square minus x square is 2x square, y square minus 3y square is 2y square. So we get 2 times x square minus y square, and what we do here, minus z dz divided by x square plus y square you can put from here, x square plus y square is minus C1 minus 4z square. So let us put that C1 minus 4z square here. Now we can integrate easily. So this is 1 by 2 times now x dx minus y dy over x square minus y square is 1 by 2 ln x square minus y square, and here what do we get? C1 minus 4z square if you put equal to t, and then C1 minus 4z square if we put equal to t, then minus 8z dz is equal to dt. So we get z dz minus z dz as dt by 8, and so we get dt upon 1. So this is 1 by 8 ln c1 minus 4z square plus some constant. Okay, so we can multiply by 8, and that will give you 2 times ln x square minus y square equal to ln c1 minus 4z square plus ln c2, and this gives you x. So we get x square minus y square whole square equal to c2 times c1 minus 4z square. Now c1 minus 4z square is x square plus y square, so c2 times x square plus y square. Okay, so this is another one, another solution. Now let us find the required surface. X square minus y square is equal to a square, z equal to 0. So x square minus y square, we are given that x square minus y square is equal to a square and z equal to 0. Okay, z equal to 0. So in the plane xy we are given a hyperbola. So here what do we get? C2 will be equal to x square plus y square. X square, so this C2 I can write as phi C1. Let C2 be phi C1. Okay, so we get x square minus y square is a4, x square minus y square is a square, so a4 equal to phi C1 into x square plus y square. Now this is what okay, so x square plus y square, and C1 is what? X square plus y square plus 4z square, that is C1. Okay, so what we get? Okay, phi C1 is equal to a4 upon x square plus y square. Okay, so we have C2 equal to this. Okay, we can write C1 equal to x square plus y square plus 4z square. C2 equal to what is the relation between C2 and C1? Let us find that. So C2 is equal to a4 upon C1 minus 4 C1. Okay, you can see C2 equal to a4 upon x square plus y square, and x square plus y square is C1 minus 4z square. So C1 C2 equal to a4. Okay, and let us now put the values of C1 C2. So we get the following. Okay, C1 C2 equal to x square plus y square plus 4z square into C1 C2 is what? X square minus y square of whole square upon x square plus y square is equal to a4. So that is the surface. Okay, x4 so we have this as the required surface. With this I would like to end my lecture. Thank you very much for your attention.